Welcome to Mystery Science Theater presents Constant Velocity. You'll recall in our experiment with the battery-powered cars, we found position and time data and we graphed it. So our position was on the vertical and the time was on the horizontal, and our graph was linear with an intercept that was pretty close to zero. We found through our analysis of the lab that the intercept of our graph represented the starting position. Otherwise known as x sub 0 or x naught. The slope of our graph, it turns out, was equal to the velocity of our battery-powered car. And so it turns out that we could find the equation of this line if we're thinking in terms of y equals mx plus b. Our y is x, that's the variable that's graphed on the vertical axis. Our slope is the velocity, we'll use v as the symbol for that. Our x, or our horizontal variable, is t, and our intercept is the starting position, x naught. And so the equation of a line for a constant velocity graph could be written as x equals vt plus x naught. We also learned other ways to represent this same motion, for example, on a velocity versus time graph. So if we graphed a velocity versus time, putting velocity on the vertical, time on the horizontal, we found that because the object had a constant slope, in other words, the slope never changed on that position time graph, that the velocity is constant as well. So when we graph a constant velocity, it looks something like this. So our velocity time graph will look like this. Again, remember our position time graph looked something like this. Velocity time graph is a constant positive velocity. And there is another way that we learned how to represent the motion, and that was using a motion map. In a motion map, remember, we have dots to represent the position of the object at 1 second intervals, and then arrows to represent the velocity. So here we have an object that is moving in the positive direction, which we will call to the right, at a constant velocity. And so on our motion map, we use a dot to represent its position, and an arrow to represent its velocity. And because it has a constant velocity, those arrows should be the same size, and the spacing between the dots should be the same each time. So here we have three different ways to represent the motion of an object. And the fourth way, which we've already talked about, is through an equation. We know that x equals vt plus x naught. So here we see four ways that we can represent the motion of an object that has constant velocity. A position versus time graph, a velocity versus time graph, a motion map, and an equation.